Newton's laws. Let's share the slides. Can you please tell me if you're looking at, oh yeah, you're looking at the slides, right? So what you have in here is a whole bunch of information that in some cases you just have to go and skim through them, but in some cases you have to pay attention to, for example, the units of the force, what does it mean, right? What is a force, which is a vector, because it has magnitude and direction. How do we measure it, right? For example, you have there the distortion caused by a force using scale or using spring, right? So we are going to be studying different forces. The main one that we are going to be introducing, or I introduced already, was the force of gravity, the weight, right? The weight is the force of gravity acting on a body. So we first start with the definition of mass in chapter 1. We continue it in chapter 2 now with the idea of weight. So weight is basically your mass times gravity, okay? And it's measured in newtons, while the mass, as you know, is measured in kilograms, or, well, the basic unit is grams, but in most of the cases we're going to be using kilograms. Now, the force of gravity is obvious. When we look around, we use those concepts to differentiate how a person walks here on Earth and how the astronauts were walking on the surface of the moon, right? Because the gravity is much less, it's 1/6 the gravity of the Earth, right? So let's remember that the weight of an object depends on two things: the amount of matter, the mass, and the gravitational pull. In this case, the gravity of the planet or moon, or in some cases, the star, right? When you get close to a star, you get a strong gravitational pull because of the enormous gravity, right? And then obviously the idea of black holes, neutron stars, and so on. Friction is another force that we should be very familiarized already, because you actually experiment it every day. When you walk, when you try to move things, right, you have a force of friction, which is the resistance to motion. You can also talk about friction for falling objects, right? If you throw an object up or down, right, there is a friction or an air resistance. In chapter 1, we neglected, right? For an ideal scenario, we neglect the idea of air resistance, right? Of air friction. However, now that we're going to be talking about masses, bodies on tables or on the floor, right? We have to understand the idea of the friction as a resistance relative to motion, okay? So remember, if you look at this picture here, we have friction due to a body on top of a table, right? And actually, for this, let's use a whiteboard for this. Okay. So the idea is that if you have a horizontal table or a floor, and you have a mass, we have to start getting into the idea of free body diagrams or forces diagrams. In this idea, we draw the force of gravity like this. This is the weight of the object, mg. All right? So when you apply a force, we know that the object will move. However, in some cases, depending how massive the object is and depending on the surface, the object may not move because there is a friction here. There is a strong friction between the mass and the body here. We call that little f or fr, just to label it as friction. All right? So the friction opposes the motion that you're trying to give. In a frictionless situation, we neglect friction. But to have a frictionless situation, it's way too ideal. We are going to be solving problems or just giving examples with no friction, but generally speaking, there is always a force of friction. And the force of friction can vary. If you have, for example, an inclined plane with some angle, the body will fall also due to gravity. But for now, let's just say that gravity is acting, right? There is a force, there is a component of gravity making it go like this. But because there is friction here, then there is a force of friction that is opposite. The motion should be going like this. But there is also friction there. Right? So that's how you draw it. How do you measure it? So to measure the force of friction, there is a whole idea of normal forces. So look at this picture here. I want to, actually from here, from Newton's third law, we know that for every action there is an equal and opposite reaction. So the weight of the object is pushing towards the floor is also pushing towards the body with what we call the normal force. This is the normal. We call it normal because it's perpendicular to the surface. In that case, the normal will be not like this. The normal will be like this. So it depends on the geometry of the problem, how you're going to find that normal, right? The normal is perpendicular to the surface. So then, is there an equation for friction? Because we have an equation if there is an acceleration, right? Newton's second law, so let's write it here, right? Newton's first law was, and we're going to recall all that, but Newton's first law was basically the law of inertia, right? A body will keep in its state of motion unless an external force acts upon it. Newton's second law states that, so second law here, that the net force acting on a body is proportional to the acceleration. That means proportional there. The equation will be F, the net force, equals to mass times acceleration. So we know this. But that's not the equation for friction though. That will allow us to find the force given the acceleration of the body. The friction that comes in two types, static and kinetic. Right? So you can have a static and static and kinetic. For the static force, the static friction, sorry, we call it F sub S. That's equal to the normal times mu sub S. And for kinetic, we call it F sub K. And that's equal to the normal times mu sub K. So you're probably wondering, what's that mu? Mu is a particular property of a surface. So a surface normally has both mu s and mu k. And as you probably are guessing, static friction is the friction due to a body that is not moving. Kinetic is the friction due to a body that is already moving. All right. So we probably won't do a lot of problems on that, but I'll show you a couple of examples. The most interesting ones are the ones on inclined planes. Those are actually very interesting because that's when you have to use the geometry of the problem. So I always find them very interesting, they actually go to the point, and we can see them here, right? So we see Fg or mg is the gravitational force, the force of gravity, the weight. But as you can see here with the plane, right, it's basically what I did on the board. You have to break, or the weight is broken into components. So we are going to learn that. Well, I mean, we'll do one so you can see, because you have to use cosine and sine for this, all right? But I think it will be very interesting, all right? And in fact, if you have seen already published week 3 extra credit problems, all right? I saw that many people did week 1, so that's good. Try to do week 2 as well, the ones with kinematics, all right? What I think I'm gonna give you as well, guys, is an equation sheet. It's always good to have one, all right? Okay, so what would you guys say about these questions? True or false? Every force that acts on anything has a specific direction associated with it. True or false? If the force is a vector, right? What do you think about this? Is true or false? Anybody?
I think it's true.
It's true. It's a vector, of course. Which of the following is not a unit of force?
Ounce?
What was that?
Ounce? No?
Ounce?
Yeah.
Yeah? Kilogram as well is not force, and tons. These should be which are not. The only one is Newton here. All right, so kilogram, ounce, and ton are not units of force. All right. The force of gravity acting on an object is called what? How do you call that?
Oh, I think this one. It's weight.
Weight. Exactly. So when this is an interesting one. The air exerts a force on a person standing in a strong wind. This type of force, friction, by the way, is example of what type of friction? Static or kinetic? What do you think? This one will be kinetic. Some people may say it's static because the person is standing, but regardless, when you guys are walking or standing, your body is moving. It doesn't matter how, right? You are walking, you can be standing, you're still the air and your body are still moving. So that's why this will be an example of kinetic friction. All right? This will be a kinetic friction example there. All right, let's recall Newton's laws. Newton's first law says that an object will remain at rest or in uniform motion, meaning in a constant speed, unless a force acts upon it. An external force, not internal forces, okay? An external force, a force pushing or pulling or lifting. All right? So we've talked about that before. That's an example of external forces. Then we have here the example of friction as well. All right? And all of those are vectors, right? And remember, a force causes a change on direction as well. Because if there is so forget about an object moving, let's suppose with some velocity, right? And then you change the direction, like you see in that example there. Then that's because there's an acceleration. And if you remember, even though the object doesn't change speeds, there can be an acceleration when there is a change of direction. The best example is what? Centripetal force. In a centripetal force, guys, which is inherent for circular motion, there is an acceleration because the object is changing direction as it goes around the circle. This happens in the merry-go-round. This can happen in a case like the one you are seeing there. Satellites orbiting the planet, right? Unless, of course, as you see there, the stream breaks and then the object leaves with constant speed. Well, it will end up losing speed because of gravity and air resistance. But the implication is that a change of speed, a change of direction does give you an acceleration, a centripetal acceleration, which hence gives you a centripetal force. All right? So an implication of Newton's first law is that the net external force must act on a body to speed up, slow it down, or change the direction. So you can make the object move faster, slower, or change direction. Because each of these is an acceleration, right? The first law will tell you that a force is required to produce any acceleration. If no force is acting, or if the forces are in equilibrium, as we're going to show you in a board in a bit, then you know that the object is static, and then the object will remain at rest or at uniform speed. That's very important, Let me give you the example I gave to AP Physics 1 last year, and it was a problem, theoretical problem, right? I asked him, what should be the force to lift a bucket of water from a well that weighs 5 newtons, with water included, to bring it up from the well at constant rate, at constant speed? Again, what should be the force that you should exert to a 5 Newton bucket with water to bring it up from the bottom of a well? What do you think is the answer? You want to bring the weight of 5 newtons up, but at constant speed, without any acceleration. What do you think? The force that you should exert is 5 newtons. Of course, in a different direction. 5 newtons goes down. It's the weight of the bucket and the water. 5 newtons will be enough to bring it up at constant rate, because the forces are in equilibrium. You have 5 newtons going up, 5 newtons going down. What's the net force? 0. And that should be the answer for this question. For an object to move with constant velocity, the net force on it must be 0. All right? How about that? That could be a question. Remember, guys, Tuesday next week, in a week from now, you have quiz number 2. All right? So that's important that you know this. All right, these concepts. Homework is already there. I know some of you have already finished it, so that's good. But there, okay? True or false? It is possible for the net force on an object to be 0, even if several forces are acting on it. What do you think? Is it true or false? That the net force on an object is 0, even though several forces are acting on it. Anybody?
False.
It's true. Look at the board. Let me show you what I did on the board. Where is it? Look at the first graph I made. There. I'm gonna say that this object wasn't moving. There was a force acting there. Right? This one. But there's also the friction. So there's other forces acting on it. The force of gravity and the normal force. There are 4 forces acting in there. And the object is not moving. The friction is the same as the force, but probably higher. And there's also weight and normal forces acting, right? So there are 4 forces, no motion. That one as well, right? I said that you can have a situation where the mass, even though it's in an inclined plane, is trying to fall, but if there's no friction, it will remain static. And there are 2 forces already acting there. All right? So it's true. Okay? It's true. The force that must act on a body moving along a circular path is called what? What's the force acting on a circular path? Anybody? It's centripetal, right?
Yeah, that one.
Centripetal force. All right, we need to review that, huh? Mass. So to talk about Newton's second law, we need to know the idea of mass, right? But this is an interesting concept. When I was doing my undergrad, in one of the textbooks, I believe this is the Tipler textbook actually, but also the professor told us that mass is yes, it's true that mass is the amount of matter. That concept is used in physics but also in chemistry. But what is the difference in the way we use mass in physics with the way they use it in chemistry? You are seeing it right now. Mass can also be defined as the measure of an object's resistance to acceleration. The more massive an object is, the less acceleration you will have with the same force, of course. Because force is proportional to the acceleration. That constant is a mass. But if you give more mass, the acceleration goes down. Right? In the equation F equals to ma, if m goes up, a goes down. All right. There you have an example, right? You have big masses, small ones, and then remember, we use the kilogram to measure masses, but that scale that you're seeing there right now is on a scale in newtons. We call that a dynamometer, right? Well, nowadays should be called more like newtometer. A dynamometer is a device that we use in the lab to measure the weight of an object with very good accuracy, actually. These scales, Newton scales, depend on gravity. In a space where if you are far enough from a planet in an empty space where there is no gravity per se, the weight will be 0, even though there is mass. On the moon, 1.6 newtons. So we're talking about 1 kilogram there. It's a 1 kilogram mass. And on Earth, 9.8 newtons, because mg is equal to 9.8. Gravity on Earth is approximately 9.8 meters per second squared. So there you are. All right. One question, and I'm gonna do this on the board because this was what Galileo discovered with using 2 different masses from the top of the Tower of Pisa. I mean, some people believe it's an anecdote only, but it's still interesting to think about it. Newton also corroborated this with his Newton's laws. If an object has a larger mass than another object, so you have a piece of iron and a piece of feather. What can you say about when they fall? Will they reach the earth at the same time? Guys, let's forget about the feather and the iron, because that was the experiment that was done in Apollo 14 in the moon, and I will explain that as well. But what Galileo did is he took 2 different balls, different masses, and he released them from the Tower of Pisa, from the top of it. And he noticed that they will reach the ground at the same time. Does that make sense? Even though they have, one has a larger mass than the other? Or can you explain it? Huh? Can you explain why objects with different masses fall at the same time? Well, there is a very easy explanation for that. We're going to use this guy, Newton's second law. When the astronauts went to the moon in Apollo 14, the third mission, Apollo 13 failed, one of them, I don't remember the name, he took a hammer and a feather. And in live television, right, he made the experiment, he corroborated the idea of Galileo. He released them, a feather, and they both fell at the same time. You know why? You're probably wondering how come it works on the moon and not on the Earth. It's because on the moon there is some, on the Earth there is something that there is not in the moon, and is an atmosphere. Because of the lack of atmosphere, there is no air friction. So that's also an interesting point. Air friction does act in daily life. We can neglect it, but there are some instances where we cannot. Like, for example, in the case of the feather. The feather will never fall at the same time of a piece of iron because of the air resistance. But on the moon it works. And let's see how it works. It's because if you have one mass, I want to call this M1, and you have another mass here, M2, and you release them, remember that gravity is acting on both. Because they are on the air, you are releasing them on the air, right? There are two forces acting. Sorry, there is one force acting on each. M1G, M2G. So yes, the forces of gravity are different because their masses are different. So how come they fall at the same rate? They are accelerating towards the ground. According to Newton's second law, the force is equal to what? Mass times acceleration. So let's write here. The only force acting is this. So I can say M1 times gravity is equal to M1A. And here, M2 times gravity equals to M2A. Aha! Look what I can do. It cancels. So A2, A1. So the acceleration for this guy is gravity. And for this is also gravity. They are falling with the same rate, the rate of the acceleration of gravity, 9.8 meters per second squared. That's why. And we use, any questions? The thing is that thanks to all of those equations and concepts, we've been able, as I said last class, to launch rockets to the moon, to put satellites in orbit, right? To study the orbits of the planets around the sun, right? By knowing things like this, right? And they were discovered 300 years ago. Anyway. What's the answer for the question that you have in front of you? The mass of an object depends on where the object is. True or false?
False.
True.
False. The mass doesn't depend where it is.
Oh,
Weight,
yeah.
the weight depends where the object is located. All right, be careful. All right, Newton's second law, we've talked a lot about it, right? It's basically the idea of objects being accelerated by an external force. F equals to ma. So you have here that a force gives you one acceleration, 3 times the force triples the acceleration by, right, the same constant, 3f equals to ma, then the acceleration will be 3 times larger than the first case. And this is where we start using the equations, right? They give you an airplane with 2,000 kilograms, is observed to be accelerating at 4 meters per second squared. What's the net force acting on it? Mass times acceleration, 8,000 newtons, right? That's an alternate statement, all right, for Newton's second law. That's very easy, right? How can we combine this with what we did before? Let me give you a situation. So, the best situation will be if you have an object that is accelerated, call it m, where the initial velocity is 0 meters per second. This is a rest. All right. In 10 seconds, the object will achieve a velocity of 72 kilometers per hour. I'm gonna do a review with you guys today, combining the units a little bit. If the mass is equal to 1,500 kilograms, so it's like a car, right? Find the force acting on it. So find the required force. All right. So we have the equation there, right? The forces, right? The net force acting on a body is equal to mass times acceleration. Again, for this type of problems, guys, we are neglecting friction for now. All right. Actually, let me see something here. Yeah, we'll do friction a little bit so you can see how it's used, because there's not much. Yeah. Okay. Force equals to mass times acceleration. We have the mass, we just need acceleration. And for that, we need chapter 2. Chapter 2, remember, the equation that you should have is acceleration is V final minus V initial over change on time. But you're giving everything, 10 seconds. So this is the time, delta t, 10 seconds. Initially 0, final though. We have to be careful with the units because the units have to be all in meters and seconds. That's in kilometers per hour. So we have to change it. And if you remember, I gave you the way to change kilometers per hour to meters per second. So 72 kilometers per hour, right? To go into meters per second, you do 1 hour equals to 3,600 seconds, and 1 kilometer, 1 hour, and 1 kilometer is 1,000 meters. Hours, kilometers. That will give you 72 times 5 over 18, which is exactly 20 meters per second. So I have my the final. So the acceleration will be using this equation 20 minus 0 divided by 10 seconds. That will be 2 meters per second square. I have that. Now I do Newton's law, Newton's second law. The force, let's use the magnitude, equals to the mass times acceleration. That's 3,000 what? Newtons. That's a nice problem there. All right. In the slides, they also give you a problem with centripetal force. I will just show you basically because it's more like an application. All right. But this one I like it because it combines chapter 2 or chapter 1 and chapter 2, right? Kinematics and Newton's laws. So there's a nice example, a review of how to convert units here. All right. So I think that's a good idea for you guys to remember. Centripetal force, remember guys, the centripetal acceleration is v squared over r. V doesn't change. And r is the radius of the loop. So if they give you a car going at some speed and some radius, very easy, you just apply the concepts of here, right? The equation m v squared divided by r, and then you get the force in newtons. Nothing that difficult, all right? So remember, right? If you are going at some speed in a loop and the speed doubles, then in this case the force doesn't double. The speed, the force quadruples, because the centripetal force acting on the car, right, is actually proportional to the force is proportional to the square of the velocity. All right. So for a car that is going twice as fast as another car, the required centripetal force will be 4 times. Okay, so that's why when you are going on ramps, you have to reduce the speed, because then if not, as higher you go, the force will get higher and higher, faster. It's not linear, it's quadratic, right? So that's important on this equation there. Now, as I said before, right? Forces, acceleration, Newton's laws, they have been used to launch the Apollos, rockets to space, right? I think we can actually skip this because we're going to talk about the units for speed and acceleration. Remember that table there, right? For distance, so it's just a recall of what we did before. For acceleration is meters per second squared. For force and weight, obviously they both are forces, the units are newtons. And for mass is kilograms. All right, so those are the units that we're going to be using, and time in seconds. So that's why in the problem that I did before, we changed hours to seconds. All right. When a given net force acts on a body, the body's acceleration depends on what, guys? According to Newton's second law. If you're pushing or pulling a body, what's the factor that affects the acceleration? The mass. Okay? The mass is the factor that affects the acceleration of a body. The mass is the resistance to acceleration, all right? The weight of an object is equal to what?
Acceleration of gravity.
Gravity, right? Yeah. Good job. This for now. Let's see what we have here. Okay, so this one we're going to skip, guys, because we didn't do projectile motion. So don't worry about this. But just if you guys are interested, okay? When we discuss motion, we could have talked about acceleration already and a little bit of Newton's laws. What you're seeing right now there is two-dimensional motion. So that's actually a more realistic type of motion. In real life, you don't just have objects moving in one dimension, up or down or left and right. You normally have them moving in three dimensions, well, four dimensions, right? But on the plane, if you project that, will be two dimensions, right? You have the vertical and the horizontal. So that's called projectile motion, because that's the motion that rockets, projectiles, baseballs, they perform, like they show you in the picture, right? The only idea, the main idea is that in that type of motion, the only force acting is gravity and is vertically down. All right? Horizontally, we ignore air resistance. So horizontally, the speed is uniform. It's constant speed. All right? And it can be modeled by a parabola, obviously. You can see there. Okay? So, just for you guys to know, that's one type of motion that we can also use to study forces and acceleration. And it's a two-dimensional motion. All right? Another motion where we have an interesting force acting, and you guys are going to do a lab on that, is this one. Hooke's law / simple harmonic motion. Let's talk a little bit about that. So when you do the lab, you understand it. Simple harmonic motion is very interesting because that's another example of another type of force that is not gravity. In simple harmonic motion, if you have ever worked with springs, or maybe we can, even though it's not really elastic, but an elastic band, right, that wants to go back to its place. But a spring is like the one that you use in your pens, right? You have a small spring, so when you click it, it opens or closes. So that is controlled by Hooke's law and then simple harmonic motion. Simple harmonic motion will be the motion itself. But Hooke's law is the idea or is the concept that allows you to compute the force. If you have a spring, there is something called the natural length. We call this L naught, natural length. Nothing in there. But as soon as you place a mass, the spring will stretch. When you do the lab on this, remember that there is a stretch that you measure from that point to the original position. That X is called the stretch or compression of the spring. Depends. You can compress it, you can stretch it. How do I find that? Because now I can say it's in equilibrium. It's not moving. Then I can pull it down and then the object will start doing this. That's simple harmonic motion. All right? Oscillatory motion, wave motion. All right? It has a period. But for now, it's static. What forces are acting here? The weight. But there has to be another force to make it in equilibrium. There is a force pulling it upwards. This is Hooke's law. That force is equal to minus kx. And what is k? K is the constant of the spring. Or we can call it the spring constant. In English, plain English, it will be the stiffness. The more stiff, the more the constant is. And that is actually very important because the way you do this lab is very easy. You just put more masses here and then it starts getting down now. So by each mass, you can compute the weight in G and then you can plot force versus distance. You get a line, the slope of the line gives you the value of the constant, right? Because you have this. If you put F on the y-axis, and obviously X is the dependent variable, the slope is K. That's Hooke's law. And Hooke's law does act in simple harmonic motion. All right? In simple harmonic motion, the see here, right? You still have the minus kx, kd. D I don't like to use. D is more for distance. X is more for the displacement, right? And we're actually measuring that. So that's what I was talking about. You plot F versus displacement, the stretch, and then the line. Ideally, you get a perfect line. The slope of this line is the constant of the spring. Okay. Now, there is also a way to find the let's see. So we can find also the period and frequency. So let's suppose you have this spring and you know the constant of the spring. As you put masses, the spring can be in equilibrium. But then, as I said, you can pull it down and the spring will start going up and down, right? So a question could be, find the period. So there is an equation for period, and I want to write it here on the board, all right? Because we do have a chapter on waves, but we don't touch much into mechanical waves and simple harmonic motion. So at least so you guys know, all right, how to get the period and frequency. That's the thing about this motion. Every motion that we have talked about today, falling objects, projectile, pushing, pulling, that's it. Straight line, circular motion, that's okay. Actually, circular also has period and frequency, but this one is a bit more obvious. Imagine you have a rope, right? And you make a wave on it. The wave will go on the rope. That wave looks like this on the plane. Okay. If you haven't done this, don't worry, but that looks very particular. That looks like a sine function. Sine and cosine in trigonometry, they are characterized by something very important. They are periodic. They have a period, which is 2 pi. But in general, the period of a sine and cosine wave is 2 pi over omega. All right? And we can write this omega for this mass spring system like this. 2 pi square root of m over k. That's where your constant of the spring and the mass comes into play. All right? The proof is very long. Not long, but it requires some calculus, so don't worry about it. Okay? How you go from W to that. You can prove that using mathematics, but that's the equation there. And then for the frequency, as you remember, we did it in chapter 1, I think, right? The frequency is the inverse of period. It's the inverse of time. So we put here the frequency, F, is 1 over this. So it will be 1 over 2 pi square root of k over m. All right? Let's do, and yes, we use sine waves or cosine to model, right? Up, down, up, down. See? Up, down, up, down. Again, we are neglecting friction or any type of friction. So we assume it's an ideal sine wave or cosine. Remember, you can go from sine to cosine. All right, they are sort of reciprocal, but let's solve a problem using a mass spring system. Okay, very simple. They give you all the information that you need. Let's leave those equations there, and we're gonna use Hooke's law to start, and then we can use those equations. They give you a mass of 0.2 kilograms connected to a spring, and they observe the displacement to be 0.3 meters. So let's suppose they give you a mass. I'm gonna draw it here. So this is the equilibrium there, and then the mass is there. They give you that this delta x, the displacement is 0.3 meters, and that the mass is equal to 0.2 kilograms. If the constant of the spring, so they give you the constant, is equal to 3 newtons per meter. So that's something I should have said as well. The units for K are newtons per meter, right? Just remember, well, from the equation, F equals to Kx, right? F is in newtons, X is in meters, newtons per meter, the units for this. The first question is, find the force that makes this happen, all right? Or actually, well, they give you, I shouldn't give you the value of K, because that's something that you should compute. Yeah. So let's find the value of K. If they give you this and this, and on top of that, you're in equilibrium here. So I'm changing the problem a little bit. We're going to use gravity. Remember, it's 9.8. To solve a problem like that, you need to remember that you have kx going up and mg going down. If that's the case, this is the key. And we're going to be going into that a little bit because something I want you guys to get out of this is the free body diagrams and equilibrium. All right? So, whatever is going up has to equal to whatever is going down. Right? If I pull it down, then it starts oscillating. No more equilibrium. But for now, it's in equilibrium. So that's why you don't need this K, because you can get it. They give you the value of delta x, they give you the value of m, and you have gravity. So look, you can say that according to Hooke's law, there should be a minus, but I'm taking the absolute value, okay? Equals to mg. Kx equals to mg. What's x? 0.3. So k times 0.3 equals to the mass times 9.8. There it is. So I can find my value of k. It's I could estimate it, but let's use a calculator. So if I use my calculator, I will get 6.5. Sorry, 1/6 there. So 5 newtons per meter. That's fine. You can get, I guess you can write to 7 newtons per meter because of 1/6 feet, 1/6 feet, 2/6 feet, 1/6 feet, so that. So that's how you get K, right? Kx, Hooke's law equals to mg in a vertical spring. And then imagine when I get a period now. So I pull it down and I want to get a period. So I use the equation over there. To get a period, what I do, I have K, I have the mass, the period, capital T, equals to 2 pi square root of m over, what's K? Oh, sorry, m was 0.2 divided by 7. And if I do that math, 0.2 divided by 7, I take the square root of that, times 2 times pi, I get 1.06 seconds. So every 1.06 seconds, the object goes back to the original position. Like back and forth, right? That's the period. So that's an application for Hooke's law and simple harmonic motion. All right. I'm just doing this because you may have. All right. Let's see this. There. Right. You may have a situation where you need to apply this either on a lab or for practical purposes. Okay. So again, if you guys are doing this, right, you have the mass in equilibrium. Equilibrium is the key. A mass in equilibrium means that it's not moving. in the case of the spring system there, the only force acting, the only forces is the force of gravity, mg, and the Hooke's law that is written on the board as well. So I make them equal to each other to find the value of the constant k. Once I find the value of the constant k, I can use it to find the period, right? Using the equation there that is written on the board. 2 pi square root of m over k. All right? They are also in the slides, but in the slides they don't show you where they come from. They just use them. So at least I'm showing you that a simple harmonic motion is a periodic motion. That's why we can talk about period. All right? It goes up and down, up and down. And you know something? To get the equations for that, we actually can make the analogy between the simple harmonic motion and circular motion. Circular motion is this. It goes there and there, right there and there. And if it has constant speed, there is period. And if there is period, then it's a periodic type of motion, right? But this one actually allows you to see a little bit more clear. Okay? So make sure when you're looking at the slides, that's example 2.4, then you're going to be able to follow it. All right? For the frequency, so once I got the period, for the frequency, you just do the inverse of the period. All right? And remember, the units for frequency are cycles per second. So how many cycles or hertz? Okay? Is the inverse of second, the inverse of period. All right? So that is for simple harmonic motion and Hooke's law. Make sure that you understand that there are different forces, right? We've talked about pushing, pulling force, lifting, friction, the force of gravity. Now we have this Hooke's law, centripetal force. All right. So you may not have to do a lot of calculation, but you may need to like describe one of them, right? So you can say that Hooke's law is the force related to a spring, and that in a simple harmonic motion it produces a periodic motion where it has period and frequency. Let's take a look again to the slides. So we don't did there it is, right? So there it is actually. That's your simple harmonic motion. All right, it can be either used as sine wave or a cosine wave. And the equation for period. And there, right, it looks like the International Space Station there. All right. Now, a body falling with air resistance. For this, again, is more in terms of the description. So the equations don't really work when you have resistance, right? Because there is a point where you reach something called a terminal speed. All right? When you are falling from the rest, there is a point where the net force is zero. So all the acceleration vanishes. And that's called, that speed, when the acceleration is zero, that's called the terminal speed of the body. That happens in fluids a lot. Let's suppose you have a glass of water, or maybe even bigger than that, like a jar, and then you let go like a piece of metal. You will see, and it's hard to do this probably, but you can see that at some point it reaches a speed, a constant speed, right? That's because the air friction, as it goes, or the friction in water as well, as you go deeper and deeper, it starts being equal to the force of gravity of that mass. When the forces are equal to each other, but in opposite directions, there is no acceleration. And that's where you get that terminal speed there. All right? That happens also in the air when we introduce air resistance. Again, it's just the concept. All right? So if they were asking you, what is terminal speed? Is the speed of a body when the net forces are acting on a body disappear, not disappear, but they are equal. Oh, sorry, when the net force is equal to 0. So all the forces acting on the body are on the same magnitude and different directions. All right. The resistance, the air resistance, is the reason why we cannot emulate the experiment from the moon between the feather and the hammer. Actually, yeah, it was a hammer. Because even though they fall at the same rate, the air resistance makes the hammer fall, or makes the feather fall more slowly. All right. So you have there a few tables with forces and the description of the type of motion. Okay. Remember that different forces can act on different environments. In a roller coaster like you have there, guys, you can have like Hooke's law, you can have centripetal force, you can have friction, right? And you can have forces due to eddy currents that we're going to study later in electromagnetism. All right, and then we're going to talk about roller coasters in energy, potential and kinetic energy, right? But that loop that you are seeing there, all right, the way you build a loop like that in a roller coaster is by measuring not just the energy conservation, which you probably have heard before, but also the amount of friction and how wide the loop can be depending on the centripetal force that you want the people to experiment. So that force that you feel when your stomach is going up in a roller coaster, when you go down or in a loop, is due to centripetal force. Right? Is the force of gravity. Is basically creating an artificial gravity. Right? So when in NASA they train the astronauts, they do make them train at very high speeds, going in loops, because it creates an apparent gravity due to centripetal forces. All right. Let me guys skip this. All right. Based on the topics we have talked today, who can give me an answer for this question? The motion of a child in a swing, going back and forth. What type of motion is that? Free fall, projectile, centripetal, harmonic motion. What do you think? That is actually a good example of harmonic motion. Back and forth. Of course, we're neglecting air friction, but still. All right? A napkin is dropped and falls to the floor. As it falls, what do you think is true there, guys? Anybody? I would say all of the above, based on the terminal speed. But you can claim that the net force on it decreases. Is the only one. It depends, right? The force of air resistance acting on it increases. I mean, it really depends on the nature of it, all right? But the one that is always true in this case is the net force on it decreases. Why? Because the air resistance as the body is falling, right, it gets bigger. So, all right. So I would say all of the above, because as it falls, also increases the speed. Okay, we can leave this one as well. And Newton's third law, guys, to finish today, is all about action-reaction. All right. When you push a wall, when you lift something, just by sitting right now, there is a force acting on you, and we can use that force to do something like the picture is showing you there, right? You can push a wall, the wall will remain still, but then you will go in an opposite direction. That's because of the force the wall is also exerting on you. All right? So remember, on the surface, this seems like a violation of Newton's second law, right? But in reality, the equal and opposite force on the wall on your hands causes the acceleration. As you push a wall, there is a force pushing you backwards. F equals to ma. All right? Action, reaction. Another way to illustrate that is rockets. The rocket goes up because according to Newton's third law, there is a force that the rocket is exerting towards the ground, right? When they are propelled, they eject combustion gases at very high speeds. This engine exerts a force that is ejecting those gases, and that force is going to the ground. And because of action reaction, it makes the object go up. The act of expelling the propellant gases yields a force that is needed to make the rocket launch. All right? All right, guys. Let's leave it here. Next class, we're going to finish with this, and then we'll do some examples and more problems on free body diagrams. All right? We're finishing with this chapter on Thursday, and then we may have time to review a couple of concepts so you guys are ready for your quiz on Tuesday. All right? Don't forget to do the homework as well on chapter 2. And are there any questions? Any questions about today's class?
Thank you.
No
Thank
problem.
you.
Okay. All right, guys. So I'll see you guys on Thursday.
Okay.
Bye-bye. See you guys later.